So another way to look at these equations is we're going to scale negative 1, 1, 2, and 1, 1, 1. We're trying to build 1, 1, 3 out of those. The problem is these two vectors, we call it V1 and V2, make a two-dimensional subspace out of R3. And our 1, 1, 3 is out here. So finding the best solution, this is really the insight that linear algebra gives us, is the best solution is going to be the m and b values that get me to the point closest to 1, 1, 3 in the space. And what I see is the scalars that I need, and the m equals 4/7 and b equals 9/7 to get to the closest point. And by plugging in here, I essentially found that closest point. So the answer is C. The closest point in this space. The best I'm going to be able to do is there C. Oh, I'm just going to do that now. So that, since I already have the calculation for C, I'll say that. And then I'll come back and I'll finish up.
So the answer to B is that.
No, the answer to C is
I'm
that.
sorry, yes.
There are, the six, the dot matrix is still universe.
That was an interesting question. We did that in a homework problem.
So you have those things in like that.
You don't have to worry about it. So in the exam, it'll have an inverse. And we talked about in class about what to do if that matrix doesn't have an inverse. And that's where I think it really starts getting interesting. Because if I had missed a lecture because of fire, I probably would have talked a bit more about that. That could have gone further. What I would have done. So I keep thinking of, oh, here's all the things that I wish I could have told you about before we get into class.
You should make a new class of all the things you wish you'd said for all the other classes.
Oh, yeah, you have no idea how much I want to do that. If I could just have 4 units instead of 3, it would be so much more. Yeah, I really hope you guys know this is not, you have here if this was the beginning of your linear algebra journey. You got the basics down, but it's a deep subject. There's a lot more to it. So this is why we care about this. Is according to the theory, there's supposed to be a straight line that connects all these data points. Of course, that didn't work out. So what we can do is say that some lines are a better fit than others. And the equation of that line is going to look like y equals mx plus b. And if I plug in this first data point, and that second data point, and that third data point, is I've got the system of equations that m and b would have to satisfy in order to be a line that goes through those 3 points. So I'm not going to be able to find an m and b to do that, but what's cool is I can find the best possible m and b. So it can't be perfect, but it can be close. And it's my m that I worked out over there. It's 4/7, and my b is 9/7. So the best straight line approximation is that one.
Where does the name least squares fit come into this?
Oh, because the way you measure how bad it is, which is essentially the same calculation you make in calculating this distance, is on this picture, it is the sum of the squares of these distances. Because the way we calculate a distance is square root of a squared plus b squared. So it's the same idea. It's the sum of the squares. 5, 5. Oh, and if you notice any typos or anything, any mistakes on the solutions to the study guides, please let me know. And of course, next semester's class is going to have the same study questions. So Tyler noticed that I had a typo on the solution to 5A part 1. So it's recently got updated. You download the current version is up. There's a correction to what I had there. Unfortunate. Just noticed another mistake. I called them P and Q on the left and F and G on the right. Should be in the same letters. So the magnitude of a vector is the square root of the dot product of that vector with itself. And we are very loosely defining vector and dot product. Some basic integration, that's x plus 1 squared. I know how to get the antiderivatives, plug in numbers, do arithmetic. So square root 7/3.
Yeah, we corrected down the, that's it, it's about
Right, it's really a 7/3, right?
Yeah,
Yeah.
7.
Right, so it's 8/3 on mine, and then Tyler showed me and verified with an online integrator that it really is 7/3. Again, if you check the new version, it's 7/3. So eventually, there's going to be no typos in that. You can help me get there. So considering x as a vector in P1, and I want to find something orthogonal to x. First of all, what does it mean to be orthogonal? Perpendicular. And how do I check that in a linear algebra way? Dot product is 0. This time it's an inner product. What does a generic P1 object look like? Yeah, it's big. Would you say mx plus b or x plus b?
I said MX plus B.
Yeah, that's what I like. So P1 is all the linear functions, all the ones that look like mx plus b. And we want to find a vector, we want to find an mx plus b. So the dot product of mx plus b with x is, and dot product for us, for this example, use this. Is that part okay? M over 3 plus b over 2 is 0. Antiderivative, plug in 1, plug in 0, subtract. And we solved a lot of equations like this. Actually, let me write it this way. A third of m plus a half of b is 0. So I showed you the trick to get to 0. So what do you want to let m be? So one vector that works is negative 1/2 x plus 1. So now, actually, you get the idea for 5. I'm going to move on a little bit. Essentially, it's just all that idea, except whenever you do an inner product, you replace it by the definition I have there. computation. We are. So 5.5b is almost identical to what we just did. We're some elementary row operations. So I'm going to replace row 2 by -1 times row 1 plus row 2. And I'm going to replace row 3 by 2 times row 1 plus row 3. 0, 0, 6. So this operation, I can't remember which type it was. This type of operation changes the determinant out. Doesn't change at all. And do you know the quick way to find the determinant of a upper triangular matrix?
What's the diagonal?
So the determinant here is 1 times 4 times 6, which is 24. This didn't change it. So that determinant is 24.